This is lesson 22 of the Quantum Mechanics, a mini lecture series, wave-particle duality part 2. Now, in just a few years after de Broglie's theory was confirmed by, was written down, it was actually confirmed by experiment, right? So for a theory to be valid, it has to be shown true by experiment. And even de Broglie himself suggested that matter waves, as they were called, might be observable in crystal diffraction experiments. That might be the way to go. Okay, like those carried out with X-rays, and I'll explain what these experiments involve. And ironically, this was first demonstrated by George Thomson. J.J. Thomson, so Joseph John Thomson's son. Okay, the guy who, English physicist who proved that the electron was a particle in 1897. So the physicist George Thomson actually showed in 1927 that electrons are actually waves. Around 30 years after his dad proved that they were, demonstrated that they were particles. And also, simultaneously, around the same year, American physicists Davison and Germer, okay, the experiment's called the Davison-Germer experiment. They accidentally showed that electrons can be diffracted. Okay, what does that mean? Well, they basically fired a beam of electrons at a nickel crystal. Okay, nickel is a metal. Okay, crystal is just a regular repeating arrangement of nickel atoms, and they observed scattering, how electrons scattered. Okay, this is diffraction, right? That's what it means. Okay, they observed a diffraction pattern identical to that observed when waves, X-rays, were fired at the crystal. Okay, so let's take the nickel crystal, let's zoom into it. If we had a super powerful microscope, here's what we would see. Okay, the dots are nickel atoms. Nickel atoms. Suppose you've got an electron beam coming in. Electron beam. You would see scattering of electrons, scattered electrons. Okay, at some angle theta. Okay, relative to this plane here. Plane is a flat line. Okay, and the distance between two parallel sets of nickel atoms in each plane. It's called a D. This is actually, so the angle theta of scattering and the distance between the two planes of nickel atoms, it's described mathematically by this relation here, 2D sine theta. This is called the Bragg diffraction relation. Bragg diffraction, named after Bragg. Sir William Lawrence Bragg, an Australian-born British physicist and X-ray crystallographer. N is a whole number. Lambda is the wavelength of radiation coming in, which is the electron beam, okay, or light. D, as I mentioned before, is the distance between the two parallel planes of nickel atoms. And theta is the angle of scattering. So you can represent it mathematically. And this relation was satisfied when the electrons were used. And it was shown that electrons scatter as though they were waves, as though they were things like X-rays. Okay, a whole number of wavelengths is needed to get the observed scattering. So a scattering pattern was observed, a diffraction pattern.